Hello everyone, today in this video we are going to talk about motional EMF, and after this video you should be able to explain the motional EMF and its cause and derive and apply the formula for motional EMF. So from our previous video we already know when a charge moves in a magnetic field it gets deflected into a particular direction. So this happens due to the force on a charge due to the magnetic field. So when we move a conductor in a magnetic field, the charge inside the conductor also moves in a magnetic field, and we already know when charge moves in a magnetic field it experiences a force. So due to the force the charge moves in one direction, due to which the current flows in the conductor, and this EMF is called motional EMF. Motional because it occurs due to the motion of conductor, and due to the EMF the current flows from one point of a conductor to another point. So the cause of motional EMF is when a charge moves in a magnetic field it gets deflected into a particular direction due to magnetic force. To derive the expression for motional EMF, we'll take a U-shaped conductor of length L, and we keep a metallic rod over this U-shaped conductor, and we apply the magnetic field which is perpendicular to this setup. Out here the magnetic field is going into the plane of the screen, and this rod can slide over this conductor. Suppose this rod is sliding with velocity v towards the left, and suppose x is the distance of the rod PQ at any time, and using Fleming's left hand rule we can find the direction of induced current. So magnetic field is into the plane of the screen, the direction of force is towards the left, so current will flow in downward direction. So this current will flow through this circuit. Using this diagram we will derive the formula for motional EMF. So as we have already discussed, this is the U-shaped conductor, and this rod PQ can slide over this U-shaped conductor. V is the velocity of that conductor, and magnetic field is into the plane of the screen. The area of the loop is given by length into breadth. Length is L, breadth is x, so area is L into x. So flux through the loop is magnetic field into area, so B is the magnetic field, Lx is the area. When we move this rod PQ towards the left, the magnetic flux through this loop will change and EMF will be produced, and EMF is given by minus d phi dt, and phi we already know, flux is B Lx, so I'll put the value, and B and L is constant, it is not changing. L is also not changing, B magnetic field is also not changing. Only the thing which is changing is x. Out here you can see when this rod moves this side the value of x decreases, so we'll get this expression. And we know dx upon dt is velocity, and the negative sign will come because when x decreases the velocity increases, so I'll put the value dx upon dt is minus v. So this is the final expression. So the motional EMF due to the motion of this rod is given by EMF is equal to B into L into V, magnetic field into length of the rod into velocity of the rod, and this EMF is produced by the motion of this rod, that's why we call it motional EMF. And the direction of induced current is found out by using Fleming's right hand rule. And if you want to find the current in this diagram, then you have to use Ohm's law. V is equal to IR. V out here is EMF, so I'll write E is equal to IR. So R is the resistance of this conductor. So this is the expression for current. Next, the power dissipated through this conductor. So we know the formula for power is V into I, potential into current. Potential out here is EMF, so I'll put the value. For I it is V by R, and E is already there, so I'll put the value of EMF, that is BLV by R, then you'll get this. So this is the formula for power. This is the question to the same derivation which we have done before, so the answer will be same as the previous derivation. So you have to assume this length to be L, this distance to be x, and v to be velocity, then you will get the same expression as previous one. So in this question, this metallic rod is moving towards our right with velocity 2 meter per second, and the length of the rod is 50 centimeter, and magnetic field is 0.5 Tesla, which is going into the plane of the paper, and the resistance R is given, that is 3 ohm. So we have to find EMF, current, and the force on this conductor. So EMF is given by this formula, so you can put, only you have to convert this length into SI unit, and for current you can use Ohm's law, that is I is equal to EMF by R. So you can put the value of EMF from here, and resistance is already given, that is 3 ohm, so you can easily find current also. So for the force is equal to BIL sin theta. So B is magnetic field, I is current, L is the length of the conductor, and out here theta is angle between velocity and magnetic field, which is 90 degree. Now in this question, this square loop of side 20 centimeter is moving through this magnetic field, and the speed is 10 meter per second, and it is coming out of this magnetic field after some time, and we have to draw the graph showing the variation of magnetic flux with time, variation of induced EMF with time, and variation of induced current with time. So this is the picture for the question, and the loop is out here, and this loop is moving 10 meter per second. So after 1 second loop will come out here, and after 2 second, after 3 second, so till 3 second there is no change in flux, so it is zero flux. So when it goes from 3 to 4, the magnetic field will enter through this loop. So you can see out here, so there is change in flux. So from 4 to 5 also there is change in flux. So from 3 second to 5 second there is change in flux, that means there will be EMF in the conductor. Now 5 to 6 second there is no change, till 11 second there is no change. Now when it goes out of this magnetic field, then the magnetic flux decreases, that means from 11 second to 12 second there is change, from 12 to 13 also there is change, after that there will be no change. So there is change in flux from 3 second to 5 second, and from 11 second to 13 second. So flux outside the magnetic field is 0 because there is no magnetic field, and flux inside the magnetic field is B into area, and magnetic field is given 0.1 Tesla, and area is 20 centimeter square. So if you convert this 20 centimeter square into meter square, then you'll get the flux to be 0.004 Weber. Now we'll draw the graph between flux and time. So between 0 second to 3 second there is no flux. Now from 3 second to 5 second the flux increases from 0 Weber to 0.004 Weber. So till here it's 0. So after that 0.004. So till 5 second the flux increases to 0.004 Weber. So after 5 second to 11 second there is no change, so the flux will be 0.004 Weber. So after 11 second, when the loop starts coming out, the flux decreases from 0.004 to 0. So it will start from 0, it will go till 0.004, again it will decrease. So now this is the graph. So from 0 to 3 second there is no flux, 0 flux. From 3 second to 5 second the flux will increase to 0.004. after that it will not change till 11 second. So after 11 second to 13 second it will decrease from 0.004 to 0 Weber. Now we will draw the graph between EMF and time. So out here you can see from 0 to 3 seconds there is no change in flux. So EMF is given by minus d phi upon dt. So there is no change in flux, so I can write it to be 0. So from 3 seconds to 5 seconds there is change in flux, and flux is changing from 0 to 0.004. So change in flux is 0.004 minus 0, and time taken is 3 seconds to 5 seconds, that is 2 seconds. So if you find the value you'll get minus 2 millivolt. So now from 5 seconds to 11 seconds there is no change in flux again. So flux is 0, EMF is 0. So now from time 11 seconds to 13 seconds flux is changing from 0.004 to 0. So final is 0, initial is 0.004. So you'll get minus into minus to be plus and the same value. So that means the EMF will go from minus 0.2 millivolt to 2 millivolt. So if you plot the graph, you will get somewhat like this. So from 0 to 3 seconds there is no EMF. From 3 seconds to 5 seconds, minus 2 millivolt is the EMF, and 5 to 11 seconds there is no EMF, and 11 second to 13 second there is 2 millivolt EMF, that is positive. So this is positive. So if you want to plot current, so you have to find the current first. So resistance is already given, so we can easily find the current, that is 20 milliampere. So when potential is positive, we'll get the positive current. When the potential is negative, we'll get the negative current. So this is the graph between current and time. Now out here you can see this is how the flux and EMF change. So you can see the flux is increasing first and decreasing and becoming 0. So this is the similar question. A square loop of side 20 centimeter is coming out of this magnetic field, and the speed is 20 centimeter per second. And we have to plot the graph showing the variation of magnetic flux and induced EMF with time. And we have to find the direction of induced current and for how long the current will exist in the loop. So if you see, so after 1 second the loop will be out here, after 2 seconds, so till 4 seconds there is no change in flux. So when it goes from 4 seconds to 5 seconds, there will be change in flux. So we got the answer to this question, that is the current will be there in the loop from 4 second to 5 second. And so to plot the graph, we can see out here, till here we have the flux. So till 4 second there is some flux that is constant. So from 0 second to 4 second, flux is not changing, while going from 4 second to 5 second the flux is becoming 0. So out here is, you can see till 4 second flux is constant, and after 4 to 5 second it is becoming 0. And similarly if you find the EMF, so 0 from 0 second to 4 second there is no EMF. So EMF will be produced only when there is change in flux. So change in flux occurs when this loop goes out of the magnetic field, that is from 4 second to 5 second. So there will be EMF from 4 second to 5 second. This is similar to the previous question, but out here the values are not given. The value of magnetic field is not given, so we can just give any value in the graph. Now this is a different kind of question in which this rod is rotating. In previous case the rod was sliding, so out here this rod is rotating around this circle, and we have to find the induced EMF across this rod, current in this rod, and heat produced in this rod. So as angular speed is given, so angular speed means 2 pi into frequency. If t is the time period of revolution, then it will cover this area in one time period. So you can see starting, so after one time period it will cover the area of circle once. So I can write the change in flux in one revolution is magnetic field into area, and area is pi L square. L is the radius of this circle. And we know induced EMF is given by change in flux by time period. So change in flux is magnetic field into change in area, that is pi L square, by time period is t. And we know 1 by time period is frequency. So instead of 1 by time period I can write frequency. Now we can put the value of frequency out here, like frequency is equal to omega by 2 pi. So using this we have got the expression. This is the EMF produced in a rod which is revolving from one point. Next, so this is the EMF. Now we'll find the current. So using Ohm's law, V is equal to IR, I is equal to potential by R. So out here potential is EMF. So if you put the value of EMF, so this is the expression for current. Now heat produced is, this is Joule's law of heating, H is equal to I square RT. So I'll put the value of current. So this is square of this into RT. After squaring you'll get this, so you can cancel this R with one of the R in denominator, and you'll get this. So this is the similar question. Out here the rod is rotating from its one point, and v is the frequency. In previous question omega was given, out here frequency is given. So if you proceed the same way that we have done in previous question, you'll get somewhat like this. So after this point you'll put 1 by time period is equal to frequency, and out here you don't need to change this frequency into omega. So from here you can find the current, taking the resistance to be R, and you can also find the force on the rod. So you know force is equal to BIL sin theta. So theta is 90 degree because magnetic field is perpendicular to the motion, and to find the power you can use P is equal to V into I. So instead of V you use EMF. So in this question there is a wheel with 10 metallic spokes, and it is rotating from its center in a magnetic field which is 0.4 Gauss. So you have to find the total EMF due to all spokes. So first I will consider one spoke. So magnetic field is given and length is also given, and now we'll find the frequency. 120 revolution per minute. So if you convert this into revolution per second, then you'll get 120 by 60 second. If you cancel this two, you'll get 2 hertz frequency. So now we can easily find other things. EMF is B pi L square V. This is the expression which we have derived in our previous question. So now if you put the value, you'll get the value of EMF. Now all these spokes are connected in parallel way. So all one points are connected out here, all other points are connected out here. So this is the parallel combination, and we know in parallel combination EMF due to this all will be equal to EMF due to 1. So total EMF is 6.28 into 10 to the power minus 5 volt. In this question, a copper disc of radius 10 centimeter is rotating with angular velocity 20 radian per second. So omega is given and magnetic field is also given. So you have to calculate the potential difference developed across the axis of the disc. So omega is given. From here you can find frequency, and you can use this expression to find the magnet. B is given, pi length, that is the radius of the disc, and V is the frequency. So this is the end of the video. Please don't forget to like the video and subscribe the channel. Thank you.